Hi, this is Dean Saputo with UV Resources, and thank you for joining us today on this presentation for mitigating disease transmission with germicidal UVC. What we'll review in the presentation will be the basics of ultraviolet light. We're going to talk about infectious diseases, specifically the inactivation of airborne pathogens. The applications are going to be airstream disinfection, or what we call in-duct or on-the-fly, upper room ultraviolet light, HVAC coil and surface cleaning. And if you're not familiar with the ASHRAE position documents, we want to certainly bring those to your attention and how UV plays a role in those documents. Finalize with questions and a review. If you take the electromagnetic spectrum and those areas that cover from cosmic rays to microwaves, in the spectrum, you have the visible light spectrum, which are colors that we can see, from violets to reds. Right above that spectrum is the ultraviolet spectrum, and it's categorized into a UVA, B, C, and vacuum, all covering from 100 nanometers up to 400 nanometers in wavelength. All germicidal lamps, whether they be off-the-shelf products like Philips, Osram, GE, any low pressure mercury vapor lamp is going to put its output out at 253.7. I've rounded it to 254 here. So all germicidal lamps that are low pressure mercury vapor will put out 253.7 nanometers right in the spectral line of UVC. Now the sun produces all of these wavelengths, but UVC is rejected off by our ozone layer. So we don't really have any UVC that makes it past our upper atmosphere. So the ultraviolet light that we're generating from low pressure mercury vapor lamps is not a tanning bed light. That kind of falls into the UVA category. It's not really the UVB section either, which is primarily responsible for skin reddening and skin cancer, both A and B are. We're the germicidal section, UVC, at the 200 to 280 nanometer range, again 253.7 nanometers specifically. And then we are not in the ozone area. Ozone's produced between the 200 nanometers, specifically at 185 nanometers. So lamps that we are providing for air disinfection will not have the capability of producing ozone. What happens at the 253.7 nanometer wavelength is that energy, the photon that is coming out of that lamp, actually breaks through a cell wall and gets into the DNA, RNA of a product. And it starts to damage the nucleic and acids and proteins and makes them incapable of reproducing. We actually cause these things called thymine dimer lesions in the DNA. You can kind of see it over here on the right-hand side. All on the same strand, breaks apart and causes this lesion. The 253.7 permanently damages it. That cell can no longer reproduce, cannot feed, it dies. The DNA in the cell starts to respond to UV energy at around 230 nanometers, maxes out at 265, and then drops back off into the 320 spectrum. So as I mentioned earlier, germicidal lamps that are low pressure mercury vapor lamps, they put their wavelength out at 253.7, which is this large red line here. It's very close to the high spectral line of 265. So now let's talk a little bit about infectious diseases. The size of the pathogen is important to us. As these products are smaller, they become to stay in the air much longer. For example, a coronavirus size, at least in the airborne side of it, has a mass mean diameter of 0.11 microns in diameter, very similar to influenza and very similar to SARS. So these particles are so small, they act more like a gas than they do a particle, so they stay stratified for quite some time. So in recent research, they found that a cough travels as far as 16 feet and a sneeze up to 26 feet. And those very small airborne particles can stay up in the air for 8 to 14 minutes. The building ventilation system becomes very important on the transmission of these small particles. If you're designing an office building, let's say an office space of 6 to 8 air changes per hour, you're going to see every 7.5 to 10 minutes the air is recirculated through the HVAC system. These small airborne particles can be brought up into the HVAC system and redistributed throughout the building. Ultraviolet energy has the ability to inactivate a wide variety of products, from fungal spores all the way through viruses, but some are more difficult to inactivate. So looking at this chart from the left to the right, some of the ones that take a little more energy to inactivate are fungal spores, bacterial spores, but some that are easier are viruses like influenza viruses, measles, coronavirus, smallpox. Those that are on the left are typically things that you would find in wet, dark, moisture-rich environments like a coil, a drain pan. However, the things on the right, the viruses, are going to be things that would be flying by in the air. In the 2009 Ultraviolet Germicidal Irradiation Handbook, written by Dr. Wally Kowalski, he has in the appendices different appendix for viruses, mold, fungi, and bacteria. What you're looking at in the background here is you're looking at the appendix for the UV rate constants for viruses. And this is all the cited studies that are talking about air, water, or surface, and it gives you what's called the rate constants of what it takes to be able to inactivate a microbe. And in there you have one, it's a coronavirus, which was a Walker 2007 study, and it gives you your K value, sometimes known also as a Z value, of how much energy it takes to inactivate this particular product, or any of those that you're seeing in the background. The K value for the coronavirus Walker 2007 is 0.377. So that becomes your multiplier, what you would use when you're doing a sizing system. Let's now look at applications of ultraviolet lights for our building. The UVC applications we'll be reviewing today will be three primary ones: HVAC air disinfection, upper air or upper room germicidal lights, and HVAC coil and surface cleaning. So we'll cover all three of these today. Let's first look at airstream disinfection. With an airstream disinfection system, we're going to need a lot more information than you would for a coil cleaning application. We're going to need to know what the airflow is. We're going to need to know what the height, the width, and the length of that space is that we're going to place the UV lights. With that, then we also need to look at the removal rate. What is it that you're looking to achieve? Are you looking to achieve a 90% inactivation, 95%, or a 99% inactivation? We need to pick the product. In this particular case, you see here's a coronavirus. It has a K value or a Z value of 0.377. That's the value that we'll use. And then that gives us the exposure time so that we can calculate out the number of lamps that you need in that space to be able to inactivate whatever removal rate you're looking for. Another way to look at it is being able to take the UVC rate constant of that specific product or multiple products, and then measuring your airflow, your air temperature, relative humidity, how long do we have exposure time to the product, that gives us dose, dimensions, height, width, depth. Is there any reflectivity we can get off of surfaces around where those lights are going to be placed? And then when we're always modeling, we want to model at the end of the life of the lamp. It's going to give us a worst case scenario, and that gives us our disinfection dose, or the dosage required for that space. What we do know is applying ultraviolet lamps inside an air conditioning system, an HVAC system, is we really want those lamps to give us a 360-degree distribution of energy. We want to be able to get the microbe coming out of the coil in this picture towards the lamp, and then also being able to expose it as it's leaving the lamp surface. So this whole box becomes our disinfection zone. So we don't want to use any type of reflectors, parabolic reflectors, anything that's going to inhibit the UV getting out in a 360-degree pattern. As I mentioned earlier, we want to talk about the ASHRAE position documents. These are important documents to read and understand, as these are the position of the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And the one on the left is the airborne infectious diseases, and the other one is on infectious aerosols. In the airborne infectious disease position document, you'll see a table called Table 1 that goes through engineering control strategies, that different occupancy categories that you see over here: healthcare, correctional, hotel, residential, retail, sports, the things that ASHRAE is recommending that you do. And those things are for everybody, for all different occupancy categories. Dilution is number one. If you can dilute, bring more outside air in, that's great. Can you change your temperature and humidity for all of them except 7, which is hotel and motels? Personalized ventilation, we're living with that now. We're living with masks and dealing with personalized ventilation. How about local exhaust? Can you exhaust more air outside? Can we increase our filters in our central system filtration? Can we go from a MERV 8 to maybe a MERV 13 filter? And can our air handling units handle that extra static pressure? Can we bring in roll in the room units, local air filtration type devices? Can we place upper room UVGI in? And again, many of the categories. Induct and air handling UVGI is another one. In-room flow regimes, differential pressurization. So in the second document, the position on infectious aerosols that came out in April of 2020, we talk again about UVGI being able to inactivate microbes by damaging the structure of nucleic acids and proteins. CDC has approved UVGI along with filters for the control of tuberculosis. And I get this was an important add to this one here was, although UVGI is well researched and validated, many new technologies are not. And I think that's important because these are, you see a lot during a pandemic of products coming out with manufacturer-driven, non-peer-reviewed data saying that these items work. And right now, ASHRAE's position is really just filters, UV lights, as we mentioned in the previous slide. A product that you may not be aware of, but we're going to cover here today is upper air or upper room UVGI. Upper air or upper room ultraviolet lights are fixtures that are mounted at least 7 feet off the ground on the wall. It can be higher, 8 feet, 9 feet, but at least 7 feet. And you want them a little bit off the ceiling by about 6 inches off the ceiling. And what you're doing is you're creating a very collimated beam that comes out of the fixture with non-reflective baffles is what's helping create that beam. So the natural air currents lift the contaminants up into the space, or even from our supply and return, the mechanical 6 air changes an hour or 7 or 8 air changes an hour help bring those very small gas-like particles up into the disinfection zone. Again, they're above the person's head, so at least 7 feet or higher. So what you're seeing in these pictures is you're seeing on the left, you're seeing a picture of a fixture in a classroom setting or in a common area. You're seeing one in a cafeteria, and you're seeing on the right-hand side one in an operatory. So again, safe for the occupants down in the room. It's a collimated beam above their heads and below the ceiling. I think this picture shows you what we just said in the last slide, that I'll go ahead and highlight it here, but what you're seeing here coming out of the fixture is a collimated beam of visible light, but also that's following the ultraviolet light. So it's down from the ceiling, up from the occupants, and a very collimated beam. And what creates that is you have a parabolic reflector, and that sends that UV energy out through these non-reflective baffles, and then again creates this collimated beam. So no one can in that occupied space is affected by the UV. The only person that would be affected is if somebody got up on a ladder and got into that very small collimated beam. Upper room UV fixtures have been around for about 80 years. The picture here on the right is actually from the 1940s, and this is for in classrooms in the United States for the control of measles. You can see them in the background here. But really, you use the upper room fixtures has been used for 80 years for tuberculosis, help control tuberculosis. It's amazing to me that 1/4 of the world's population is already infected with tuberculosis, and we have 1.5 million deaths per year. The inactivation rate of a coronavirus and a tuberculosis are not much different. So if you size a system for tuberculosis, you can easily size it for a coronavirus. One of the studies that Dr. Shelley Miller did from Colorado State University looked at applying upper room UV and being able to see what the equivalency of air changes per hour were. So an example, if we're doing something with 40 microwatts, which is a typical we would do for a tuberculosis application, that has an equivalency of about 14 air changes per hour. Again, these can be in the room with the patient, with the doctor. They're running 24/7 if it's a hospital setting. This is a pre-op over to the left where they have them right before going into surgery. Again, safe for occupants in the room. The biggest factor is to make sure nobody gets up into that zone. One of the things we haven't covered and we don't want to get away from here is the ability of ultraviolet lamps to clean coil surfaces. By placing UV lights in and around the cooling coil section, and specifically on the downstream side of the coil, we start to work that UV energy down into the packed depth of the coil. The UVC energy has a very high reflectivity off of surfaces that are made of aluminum, and with cooling coil fins being made mostly of aluminum, we can start to send the fluence or the energy down into that packed depth, breaking down the biological biofilms, the microbial growth that's in the inside, and dislodging the dirt and other things that are held to it. So in a very short period of time, you start to see things happening with these coils. You start to see a lower pressure drop, you start to see an increase in airflow, and you get a better heat exchange efficiency. As I mentioned in the previous slide, the best location for UV lights would be on the downstream side or air exiting side of the cooling coil. It's a perfect location for us because we can not only take care of the cooling coils, but we can take care of any contamination that might be in that drain pan. A couple of years ago, ASHRAE funded a study called Research Paper 1738 that took a look at several air handling units where they studied these, measured these air handling units for an entire year, added UV lights, and then measured them for another year. And it was looking at what the costs were to add the lights, how much energy consumption they consumed, how much energy they saved, maintenance costs, but very importantly, the collateral health benefits of what happens with clean coils, specifically for indoor air quality. So this is the coil that we saw in the previous slide. And when they activated the UV lights, they went to the opposite side of the coil and tried to take a picture of how much of the visible light came through the coil. And then at the end of the study, they did the same thing, which is the picture on the right. But remember, this was an energy study. So what they did measure was about a 21% decrease in just the pressure drop and a 14% increase in the overall heat transfer. So if you start to put those into an energy calculator or return on investment, it's very affordable to be able to put lights in and be able to pay for them in a very short period of time. So wrapping up here, let's go back over and review some of the things we talked about. Summarizing the placement of UV lamps in an HVAC system, there's really just a couple places that you'd want to place it. If we were talking about coil irradiation, it would be on the downstream side of the coil. And again, what we need to have here is the measurements of the height and the width of that space. Height and width gives us enough information to be able to size a system for you for coil irradiation. We're going to talk about here in a second about air disinfection, and air disinfection can be either on the upstream side of the cooling coil, warmer air, the lamps perform a little bit better, or they can be put on the downstream side of the coil and you can get both the benefit of coil cleaning as well as air disinfection. As I mentioned in the previous slide, the air disinfection, we can be placing lamps inside the HVAC system. Again, what you're seeing here on the right-hand side is a picture of an air disinfection on the downstream side of a cooling coil. Maybe it's going to be something inside of a duct where we need to know the information from the duct. And particularly, we need to know what is the height, width, and depth, what is the target microorganism, what is the construction of the material of that duct or that plenum, what's the airflow and the temperature. And that gives us enough information to guide you with the number of lamps on whatever removal rate you are looking for. For sizing upper room or upper air UVGI, we just need to know the ceiling height. What is the height of that ceiling? We need to know what the width of the room is and what the length of the room is. So sizing for coil clean, what we really need to know is the dimensions of the downstream side of the cooling coil. We'll need to know the height and the width of that space. These lamps are put around 36 to 40 inches apart, as you can kind of see in the drawing here. So just height and width of that space allows us to give you a product selection. Ultraviolet lights have been successfully used for over 100 years in water applications. We have 80 plus years in upper room or upper air UV lights, 30 plus years of proven in-duct applications, whether that be for air disinfection or for coil disinfection. I recognized in 2 ASHRAE handbook chapters, that's applications and the systems and equipment handbook, 2 methods of test standards, 185.1 and 185.2, 3 position documents. We talked about 2 during this presentation: airborne infectious diseases, infectious aerosols, but also take a look at the filtration and air cleaning position document, as that has some good information on other technologies as well. Extensively peer-reviewed. We have over 100 years worth of peer-reviewed studies on this technology. And remember that other disinfection technologies are not well researched or validated. Thank you for joining us today for this presentation. Should you need additional information, please contact us at UV Resources, and our email is info@uvresources.com. In addition to the references that were throughout the presentation, we have summarized the references here in the following slides.